Today, we'll delve deeper into the study of a phenomenon that is both violent and vital in the grand cosmic plan, the collision of planets. The cataclysms in which planets collide and merge are not just spectacular shows of cosmic fireworks, they are the architects of worlds, the creators of moons, and perhaps the creators of life itself. It is here, amidst the chaos of colliding worlds, that we find the solution to our planet's past and the mysteries of other solar systems. Our story begins about 4.5 billion years ago with the colossal impact that gave birth to the Earth and its faithful companion, the Moon. Imagine two similar planets in the same orbit, pulled together in a cosmic embrace. This grand collision not only formed the Earth-Moon system, but also set a precedent for understanding the formation of planets in the universe. Recent astronomical observations, thousands of light-years away, have recorded a similar but much more dramatic event. Two giant planets, like Neptune, collided at astonishing speeds. This collision was so powerful that it caused the light of their own star to be attenuated by a staggering 95%. Such observations make new adjustments to our understanding of cosmic events and indicate that planet collisions may be far more common than previously thought. From the birth of satellites to the mysteries of planet formation, today we'll witness the power of gravitational entrapment, unravel the history of our Earth and Moon, and look into the future of space exploration. Across the vastness of the universe, the birth of satellites is a tale of cosmic creativity. Satellites, or moons as we often call them, are born in many different ways, each telling a unique story of celestial mechanics and cosmic chance. One of the main ways in which satellite formation occurs is within the circumplanetary disk. This disk, composed of gas, dust, and debris, orbits around young planets like a miniature solar system. Over time, the material in this disk coalesces, giving birth to moons. The classic example is Jupiter's Galilean moons, Io, Europa, Ganymede, and Callisto. These moons formed from the same disk that surrounded Jupiter when it was young, a process mirrored in miniature throughout our solar system. Another intriguing challenge is gravitational entrapment. This event occurs when a wandering celestial body, attracted by a planet's gravity, becomes trapped in its orbit. Neptune's moon Triton is a prime example of this. Astronomers believe that Triton, with its retrograde orbit, was captured by Neptune's gravity. And now, the interplanetary vagabond is locked in endless tandem with its host planet. Finally, we explore the third, a violent but creative process resulting from the collision of giant planets. This scenario resembles a celestial race for survival, where the consequences of such colossal collisions can lead to the formation of moons. The origin story of our own moon is believed by many scientists to be the result of such a cataclysm. About 4.5 billion years ago, a Mars-sized body called Theia collided with the young Earth. The debris from this massive collision eventually coalesced to form the Moon, our permanent satellite. Each of these processes formation in the near-planetary disk, gravitational entrapment, and the consequences of planet collisions provides evidence for the dynamic and often tumultuous history of planet formation. Let's take a closer look at the thrilling spectacle of gravitational entrapment, the very process when a celestial wanderer, drifting in space, is captured by the gravitational pull of a planet, changing its fate forever. One of the most intriguing examples of this cosmic phenomenon is Neptune's largest moon, Triton. Unlike most moons in our solar system, Triton orbits Neptune in a retrograde direction, a clear sign of its dramatic past as a captured object. This unusual moon, with its icy surface and thin atmosphere, was likely a free-floating object in the Kuiper belt before Neptune's gravity drew it into orbit. The Kuiper belt is the region of the solar system beyond the orbit of Neptune. Although the Kuiper belt is similar to the asteroid belt, it's about 20 times wider and 10 times more massive than the latter. The secrets of Triton's capture are not limited to its orbit. The event had a profound effect on both Triton and Neptune itself. The capture resulted in enormous tidal forces that altered Triton's internal structure and may have given rise to its geologic activity. In addition, it may have altered Neptune's orbit and axis of rotation. Capturing Triton is not only the story of the Moon, but also a window into the composition and evolution of celestial bodies in the outer solar system. By studying Triton, scientists can gain insight into the composition and characteristics of other Kuiper belt objects. Its icy surface, with its nitrogen geysers and thin atmosphere, provides insight into conditions in this distant region of our system. The implications of Triton's capture extend to our understanding of planetary systems beyond our own. Such events can dramatically change the dynamics of a planet's moons and rings. This shapes our understanding of how satellite systems evolve and influences the search for similar phenomena in exoplanetary systems. A secret it shares with its closest celestial partner, the Moon. The story of their birth is a story of cataclysm and creation, which determined the fate of both bodies as a result of a monumental event, the collision of planets. According to the giant impact hypothesis, about 4.5 billion years ago, a Mars-sized body called Theia collided with the young Earth. This colossal impact was not just an impact, but a catastrophe whose energy was enough to melt and vaporize both Theia and much of Earth. After this cosmic cataclysm, a disk of debris, consisting of parts of Theia and Earth, revolved around the molten planet. Over time, these fragments fused together under the force of gravity, giving birth to our Moon. The Earth, too, was forever changed. Its composition, axis, and orbit were altered by this collision. The evidence supporting this hypothesis lies not only in theoretical models, but also in tangible evidence. Samples of lunar rocks, brought back by the Apollo missions, are strikingly similar in composition to Earth's mantle, suggesting a common origin. In addition, computer modeling of this event accurately matches the current orbital dynamics of the Earth-Moon system. This theory has profound implications for understanding the history of the Earth itself. The impact probably played a crucial role in shaping the planet's geology and possibly even its ability to harbor life. By stripping the Earth of some of its primordial atmosphere and altering its rotation, the impact may have laid the groundwork for the unique conditions that support life as we know it. Thus, when we look at the Moon, we are looking not just at a satellite of the Earth, but at a part of our planet's past, a celestial body, born out of one of the most dramatic events, at least to us, in the history of our solar system. Among the accounts of the formation and evolution of our cosmic neighbor are other often overlooked consequences of planetary collisions. These events not only shape the planets and their moons, but also leave behind characteristics and phenomena that further define the character of these celestial bodies. One such consequence is the formation of planetary rings. These beautiful and delicate structures, which often adorn gas giants such as Saturn, may be the result of collisions. These rings, although not formed directly from a single massive collision, are believed to be the remnants of smaller and more numerous events. From tiny ice particles to large chunks of rock orbiting Saturn, these bodies create the iconic appearance that we see today. Such rings are not unique to Saturn. They are a common consequence of collisions in planetary systems. A peculiar axis of rotation is a prime example. Astronomers suggest that a massive collision with an Earth-sized object in the distant past may have flipped the planet on its side, resulting in its extreme axial tilt of about 98. This tilt accounts for the planet's incredibly contrasting seasons and unusual magnetic field. Coming closer to home, Mars presents another intriguing case study. The Borealis Basin, a huge impact crater that occupies most of Mars' northern hemisphere, is thought to be the result of a colossal impact. The red planet also has a smooth, flat northern hemisphere, in stark contrast to the heavily cratered southern hemisphere. This dichotomy suggests that a powerful impact occurred in Mars' past, altering its surface and possibly also affecting its internal dynamics and, subsequently, the planet's climate and atmosphere. Even Venus, our sister planet, bears traces of a history of collisions. Its dense atmosphere, composed mostly of carbon dioxide with thick sulfuric acid clouds, raises questions about its past. Some theories suggest that comet impacts may have contributed to the dense atmosphere by delivering volatile compounds. These events may have created the greenhouse effect on Venus that led to the current inhospitable conditions. Each of these examples once again convinces us that even on such giant scales, collisions are far from rare. They continue to shape the physical characteristics, atmospheres, and even climates of planets, leaving an indelible legacy in their evolution. In the relentless pursuit of understanding the universe, astronomers have quite recently captured an amazing event, the potential collision of two giant planets. This unusual observation not only strikes our imagination, but also provides insight into the dynamics of planet formation and the evolution of stellar systems. Late last year, astronomers investigated observations made in 2021, an unusual phenomenon around the young star Azasan 21Q. This star, located about 1,850 light-years away, showed all the signs of such a grand event. The evidence significant infrared brightening and a complex optical eclipse indicates a colossal planetary collision. The infrared enhancement of the star, corresponding to a black body temperature of 1,000 Kelvin and lasting about 2.5 years, was superimposed on a wavelength-dependent optical eclipse lasting about 600 days. These observations led researchers to hypothesize the collision of two exoplanets, each with masses ranging from a few to tens of Earth masses, located at a distance of 2 to 16 astronomical units from the star itself. Such a collision is a spectacle of cosmic proportions. Imagine two planets, presumably similar to Neptune, being attracted to each other by gravity and colliding at high speeds. The consequences? A debris cloud that attenuates 95% of the star's light, and an incredibly hot, glowing remnant visible in infrared light. The significance of this event goes far beyond its awe-inspiring visual impact. It provides a glimpse into the rare processes that form young solar systems. These giant collisions, predicted by theories of planet formation, play a crucial role in determining the architecture of planetary systems. The study of Azasan 21Q is a testament to the importance of continuous astronomical monitoring. Such observations allow us to record these fleeting but informative events, shedding light on the dynamics of planet collisions and their role in the formation of solar systems. Events occurring during the early and turbulent stages of stellar system evolution play a key role in shaping the characteristics of planets and moons. At the stage of the birth of a star system, space is a crowded, chaotic place. Planets, planetesimals, and debris are in constant motion, often colliding and merging. These collisions can lead to the formation of larger planetary bodies, changing their orbits, composition, and even atmospheres. Take our Earth, for example. Its collision with Theia not only led to the formation of the Moon, but also contributed to the tilt and speed of the Earth's rotation. This impact may have played a crucial role in the formation of Earth's stable climate, which eventually became the basis for life and our existence. The recent observation of the star system Azasan 21Q emphasizes the significance of these events. This colossal collision provided a huge debris cloud. Following this discovery, it becomes more apparent that such events, while dramatic, are not rare anomalies, but instead form an integral part of the evolutionary narrative of stellar systems. Planetary collisions can have a variety of consequences. They can strip a planet of its atmosphere or promote its development, affect its magnetic field, and even determine its potential habitability. The moons formed from these collisions carry the legacy of their parent planets, providing clues about the history and evolution of their systems. Collisions also play a role in the redistribution of materials within the solar system. Elements formed at the heart of stars disperse and recombine, contributing to the diverse compositions of planets and moons. This cosmic recycling is fundamental to understanding the diversity of worlds we observe in our galaxy. We've already moved into a new era in astronomy, and the future of research and discovery in planetary collisions holds great potential. Continued advances in technology and ambitious space missions have the potential to revolutionize